We are in chapter 5, which is on shear. This is the 40th session overall, and we discuss unsymmetric loading of thin-walled members and shear center in this session. This is the roadmap of the first 4 chapters. Hence, a background has been given based on which we are discussing the chapter on shear. Equally, bending and shear are inseparably linked. This is the 4th session out of 6 sessions in shear. Till now, we have dealt with structures with 2 axes of symmetry. Here we'll deal with unsymmetrical loading of thin-walled members. We'll also discuss shear center. This session is on theory. In the next 2 sessions, we'll look at examples. We'll now look at the shear case for unsymmetrically loaded thin-walled members. First, we'll deal with sections with one axis of symmetry and then sections with no axis of symmetry. One would remember that the shear formula we obtained was based on the flexure formula. So the restrictions of the flexure formula applies here as well. Here we have a channel section which has one axis of symmetry. A load is applied along the axis of symmetry. The flexural formula is applicable and the shear stress formula is also applicable. So we can determine the shear stress in the section using the shear formula for this case. In figure 2, this axis is perpendicular to the axis of symmetry and passes through the centroid. If a load is applied along this axis, then determining the shear stresses in the section is more involved, as we shall see. Let us start our investigation by assuming that the shear stress formula is applicable. We can then find the shear stress and the shear flow in the channel section. Consider section 1.1. Then the shear flow will be given by taking the statical moment of area of this small portion. Consider section 2.2. Then the shear flow will be given by taking the statical moment of area of this portion, which is slightly larger. Consider section 3.3. Then the shear flow will be given by taking the statical moment of area of this larger portion. So the shear flow will increase as we move away from the edge. The shear flow in section 4.4 will be still higher. The highest shear flow will be at the neutral axis. Now consider the lower leg. In order to find the shear flow in section 1-1, we have to use the statical moment of area of this small portion. To find the shear flow of section 2-2, we have to use the statical moment of area of this portion. The shear flow in the lower leg will be equal in magnitude to the shear flow in the top leg, but oppositely directed. So this will be the overall shear flow. When discussing an I section, we mentioned that the variation of shear stress and shear flow in the flange was linear. So from O to A, The variation of shear stress and shear flow will be linear as shown here. Also, from O' to C, the variation of shear stress and shear flow will be linear. In the web, the variation of shear stress and shear flow will be parabolic. This figure gives a schematic diagram of the variation. In the last slide, we used the shear formula to find out the stresses in the flange of the channel section and also in the web of the channel section. We also found out the variation of shear flow. This is a schematic diagram. Now from the shear stress and shear flow, we can find out the forces acting on the arms of the channel section and also on the web. Consider this point as A. Then F1 is equal to QAB divided by 2 or tau A PB divided by 2. The force F2 is oppositely directed to F1 and of equal magnitude. We can also find the force in the web. So V is equal to integration of Q dy with limits minus h by 2 to plus h by 2 or tau P dy with limits minus h by 2 to plus h by 2. From these two forces, we see there's no net horizontal force acting on the section. There is a vertical force P acting on the section. These two forces create a moment about point C, F1 into h. Also, the vertical force V create a moment P into A about point C. So there's a moment acting about point C. We were looking for a solution to this problem and we applied the shear formula. With the forces that we are getting, however, there's a moment about the point C where the load has been applied. To understand the position we are in, let us consider the case of a load applied to the face of a pin. So this is our problem. The load is applied as shown and we want to find the stresses in the section A. Let us think that we assume that we can solve the problem by applying load at the centroid of the section. This will create an uniformly distributed stress at the section A. The resultant of these stresses will act through the centroid and create a moment about the point G. Here we'll use the formula P divided by the area. Similarly, here we are using the shear formula and we have ended up with the moment about the point C. This problem is similar to this problem. Even though the load is applied at the centroid, there's a torque acting on the section. Just like a moment is acting at the section A. We need to find a separate point about which, at which if the load is applied, there will be no torque in the section. That separate point is called the shear center. So this load is eccentric like this load, and this section will be subjected to both shear and torque. For this problem, we'll get the stress at AA by using the formula P divided by area and adding the stress due to the moment. Similarly here, we'll get the stress at the section 1,1 by using the shear formula and adding the stress due to the torque acting on the section. The stresses in section 1,1 is shown in this figure. These are the stresses due to shear. There are extra stresses due to torque acting on the section. We earlier considered the case of a vertical load being applied at the centroid of the channel section. Consider a section 1,1. If a vertical load was applied at the centroid, then we saw that the section will be subjected to both shear and torque. Now, if we keep on moving the point where the vertical load is applied, we'll reach a point where if the load is applied, there is no torque in section 1,1. Point where that line of action cuts the axis of symmetry is called the shear center. Here we denote the distance of the middle of the web, that is the horizontal distance, to this line of action as E. If the load is acting through the shear center, then there will be no torque in section 1,1. So the shear stresses will form these forces on the flange and the force given here on the web. Here the portion to the left of 1,1 is given. In this figure, we have rotated this left portion and we are viewing it from the section 1,1. This is the view that we get. We can find the horizontal distance E of the shear center. Since there's no moment at the shear center, V into E must be equal to F1 into H, from which we get E is equal to F1 into H divided by V. This line of action is parallel to the line of action of the principal centroidal axis earlier considered. If we consider a section 1,1, then with this line of action, the normal stress created will be such that there will be no moment about the y-axis. Also, as we have seen, there will be no torque or moment about the x-axis. The role of the shear center when shear force acts is similar to the role of the centroid when normal stresses act. So it is helpful to draw an analogy between centroid and shear center. Consider this rectangular beam subjected to a force acting on the centroid as shown. We take a section AA. Then uniform normal stresses will act on the section as shown in this figure. The section can be divided into 4 quadrants. In the quadrant A, B, C, D, the stresses can be represented by a force R1 as can be seen in figure 1c. In the other three quadrants, the resultant forces can be represented by R2, R3, and R4. Consider the moment of the force R1 about the point C and the force R3 about the point C. They are equal in magnitude and cancel each other. Consider the moment of R2 about the point C and R4 about the point C. Again, they are equal in magnitude and cancel each other. So there's no net moment at point C due to these four forces. Here we have a shear force acting at the shear center. It is similar to a normal force acting at the centroid C. We consider a section AA. Similar to the way that this normal force created normal stresses, here the shear force creates shear stresses in the section AA. The stresses acting here can be represented by four resultants as shown here. Similarly, the stresses acting in this channel can be represented by three forces. The moment of these four normal forces about point C is 0. Similarly, the moment of these three forces, which are due to shear stress, about the shear center is 0. Consider the case where this force is not applied at the centroid. Then this eccentric force can be represented by a force applied at the centroid and a moment. So section AA is subjected to stresses due to an axial force and a moment. Similarly, consider a case where the shear force here is not applied at the shear center but at a distance E1 from the shear center. Then the section AA will be subjected to both a shear force and a torque. We earlier discussed that if we have a vertical force applied as shown, either acting on the centroid or along the web of the channel section, then there will be a torque on the channel section apart from shear force. If we apply the vertical force at the shear center, then there will be no torque acting on the channel section. Here we have taken a section 1-1, and this diagram shows the portion to the left of the section. The forces acting on the channel section, these two horizontal forces acting on the flange and this force acting on the web. Here we have shown this portion from the other side and after rotation. So the internal forces are shown. The forces acting on this face in figure C and in figure D are statically equivalent. In figure D, we have added two equal and opposite forces. This distance is E, and V into E is equal to F1 into H. which means that these two moments cancel each other. Figure E is equivalent to figure D. So we are left with one shear force acting on the section. Figure A and B show the shear force acting on the shear center. That is the external force acting, which is shown in this figure E, and this is the internal force acting. So the channel is in equilibrium due to external and internal forces acting. Earlier we mentioned about external forces, internal forces, and stresses. In the case of axial loaded structures, structures subjected to torque, and structures subjected to bending. The case of shear force and stress can be aligned in a similar way. So consider this as the external force. Then, by taking a section, we have the internal force. Now, the forces in section 1.1 is equivalent in figure D and figure E. Two sets of forces causing with couples been added in this figure. This figure D is equivalent to figure C. Thus, in figure C, we have removed these two equal and opposite forces acting on the shear center. As we have earlier seen, these forces can be represented by these shear stresses. So here we have moved in reverse and shown that the shear case aligns with the axial load, the torque, and the bending moment case. In the last slide, we considered the force acting at the shear center. Here we have a force acting on the flange. At a section 1.1, there's a equal opposite reaction force acting as shown. This force can be moved. So here we have the force acting at the shear center along with the torque. So these two cases are equivalent. Similarly, this internal force can be moved. So we have a force and a torque acting as shown. In this diagram, the external force has not been moved. In figure 1C, we have added two equal and opposite moments to figure 1B. So they are statically equivalent. The two equal and opposite moments are F1 into H and V into E. So there are these forces and a torque acting at the section. These two forces are equal and opposite, and in figure 1D we have removed those two forces. So figure 1D is statically equivalent to figure 1C. There is still a torque acting as shown. The forces in the flange and web of this section are due to shear stresses. Due to the torque acting, there are additional shear stresses acting in the section. As earlier mentioned, this case is similar to the case shown here. So we have a rectangular section and a load is applied at the centroid along with the moment. Consider a section CC. Then it will be subjected to stresses due to the centroidal force and also due to the moment. This is similar to the case shown in figure 1e, where the stresses are due to the shear force and also there are additional stresses due to the torque. We earlier discussed the way the shear center can be obtained for a channel section. The force F1 is tau d E into B divided by 2, where D is this point. The force V in the web is related to the shear stress in the web. For equilibrium, V is equal to P, and we can find out this distance E using this equation. For a section with two axes of symmetry, the shear center and the centroid coincide. For a section with one axis of symmetry, the shear center is on the axis of symmetry but at a distance from the centroid. For a section with no axis of symmetry, the shear center is generally distant from both the principal centroidal axis. For a section with one axis of symmetry, a force can be applied in any direction at the shear center. This does not cause any torque in the section and the shear stresses can be determined. We can resolve this force into Py and Pz as shown. We can use the shear stress formula to find stresses due to Pz, and we have just discussed that we can use the shear stress formula for Py. We can then sum up the stresses. Here we look at a channel section which has no axis of symmetry. We'll find the shear center. We'll also determine a process of finding shear stresses. The principal axis that passes through the centroid for this channel can be determined. If loads are applied along the principal axis, then the flexure formula can be used. The shear formula is based on the flexure formula. We'll carry out the analysis of the angle section similar to the analysis of a channel section with one axis of symmetry. With the channel section, we initially considered that the load was applied along this principal centroidal axis, though in this figure the load has been shown applied to the shear center. We then found out the shear stress and the shear flow in the channel section. After that, we found out the forces in the different portions. If we consider the centroid, then these forces create a moment about the centroid. So, if the load is applied along this principal centroidal axis, there's not only shear force but also a torque acting on the section. We next found out the position where if the load is applied, there will be no torque in the section. The moment of these forces above the shear center is zero. Here the angle has been rotated, so one principal axis is vertical and the other principal axis is horizontal. Let us consider that we apply a force along this principal axis. Then this principal axis is the neutral axis. We can find shear stress and shear flow along the length of the section. To find shear flow in section 1-1, we consider the statical moment of the area of this portion. To find the shear flow at section 2-2, we consider the statical moment of area of this larger portion. In this manner, we can find the shear flow along the length of the two legs. If we consider a small length along the leg, then QBS would give dF, the force for that small length. All these small forces create a force F1 in the longer leg and F2 in the shorter leg. We can see here that we found a point about which these forces have zero moment. Consider a point here where the two forces intersect. Then the two forces will have no moment about this point. Then, like this point is the shear center. Consider a force applied parallel to the principal centroidal axis passing through this point. Then it will induce forces in the two legs such that the resultant is equal in magnitude and opposite in direction to the applied force. There will be no torque acting on the section. We can switch principal axis. So if a force is applied parallel to the other principal axis and passes through the shear center, there will be no torque in the section. As in this case, we can use the shear stress formula to find the stresses in the section. So in general, a force can be applied in any direction at the shear center and it will cause no torque. This force can be resolved along the two principal axes or parallel to the two principal axes. We can use the shear stress formula to find the shear stress for each of these cases. These shear stresses can be algebraically added up to give the shear stress in the section. Here we have found out the shear center for an unequal angle. For any section which has two thin intersecting rectangles, the shear center is located at the joint. In the earlier slide, we looked at the problem of an unequal angle subjected to load from one side only. A three-dimensional view of the angle subjected to load would help us understand the problem. So here we see a load acting at the shear center. The load is considered to act in the YZ plane. Consider a section 1-1. The load will create stresses in the section, and due to the stresses, there's a force F1 and F2 acting on the two legs. The resultant of these two loads is a force that is equal and opposite to the external load. This resultant also acts at the same point in the section. Although the external load and the resultant act at the same point, they are separated by the length at which the cross-section has been taken. So they do not act at the same point. We now consider a Z section which has no axis of symmetry. We find the two principal axes that passes through the centroid. This point O is also called the center of symmetry. If a point is the center of symmetry, then if we take a point 0 in the section and pass a straight line from 0 through O, then it will intersect the section at point 0 dash. The distance 0 O will be equal to O 0 dash. Here the diagram is schematic, so we have to assume what we just mentioned. Similarly, if there's a point 1, then if we pass a straight line from 1 through O, then it will intersect the section at 1 dash, so that 1 O will be equal in length to O 1 dash. Again, here we have to assume what we just mentioned. So any point in the section passing through the center of symmetry has an equidistant point in the section on the other side. If we apply the load along the principal axis, then the flexure formula is applicable. The shear formula is based on the flexure formula. For the force applied along the principal axis, we can find out the shear stress and the shear flow using the shear formula. Consider section 1-1. Then we need the moment of area of the portion 0011 to find the shear flow. Consider section 2-2. Then we need the moment of area of 0022 to find the shear flow. The second moment of area will be larger, so the shear flow will be larger. In this way, we can determine the shear flow of the entire section. From the shear flow, we can find the forces. So there will be two forces F1 of equal magnitude acting on the flanges, and there will be a force F2 acting along the web. These two forces F1 are also equidistant from the point O, so they create no moment about the point O. They can be represented by an equivalent force 2F1 passing through the point O. These two forces F2 and 2F1 both pass through the point O, so they create no moment about point O. So the center of symmetry is also the shear center for the Z section. As in the case of an unequal angle, a load can be applied in any direction passing through the shear center. We can take components of the load along the two principal centroidal axes. We can then find out the shear stresses in the section due to each load, and we can add up the shear stresses algebraically, get the final stresses in the shear section. Here again a three-dimensional diagram is shown. The load is applied at the shear center in any direction. We get forces in the three different portions whose resultant is equal and opposite to the external load. However, the resultant and the external load are separated by a distance. It is to be noted that in a Z section, Like the section with two axes of symmetry, the shear center coincides with the centroid.